Well, I found this funny cartoon with the student's t-distribution, and I guess didn't pass. So, if a data fails the teacher's t-test, you can just force it to take the test again until it passes. So that's the joke. All right, so we are revisiting the model for sampling distribution of the means. This time we're going to be doing a one sample t-test. So your test statistic, which is going to be like your z-score, but it's t here, is pretty much the same. You take your sample average minus your mean divided by your standard error for the sample. Just like before, our standard error for the sample is s divided by square root of n. We're going to use the student's t model with the degrees of freedom equals n minus 1 to get our p-value. So let's go ahead and look at an example. We've got some coffee cups, and a coffee machine dispenses coffee into the paper cups. You're supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. Here are the amounts, all right, and measured. We have a random sample of 20 cups. Is there evidence that the machine is shortchanging customers? So first of all, let's start with our hypothesis, which is that the machine is just normal, and it's not shortchanging customers, and its average is 10. If it's shortchanging customers, it's giving them too little coffee. So our alternate hypothesis is that there are less than 10 ounces in a cup. Okay, so let's go ahead and see if we can use our model. Is it random? Well, it is given in the problem that it's random. Independence. There's reasonable to think that one cup does not influence the other. And then the nearly normal condition. Well, here's the histogram of the data, which we did last time, and the data looks roughly unimodal and symmetric. All right, so now the mechanics and calculations. So first of all, we did one var stats, so you can get your mean and your standard deviation for your sample. And it's 20. It's nice your calculator tells you that, which means our degrees of freedom is 19. We need to calculate the standard error for the mean, so we divide this by the square root of n, and we get 0.044. Now we need to calculate our test statistic. So we go our mean minus what we're testing against, our parameter, divided by our standard error, and we get a t-value of negative 3.49, which sounds pretty darn far away. And in fact, if you use a t-table, you can look it up, and you will get that the probability is only 0.0012 or less than 1%. The easier way to do this is to use the t-test under stats test. So you go ahead and scroll over to test, and you can see it's the second option right there, t-test. The nice part is with the data, you can just put in the mean, and you have your list. I'm using list 2, or list 1, I'm sorry. And I just want to see if my alternate is actually that it's less than 10 ounces, so I'm saying less than. And I personally love the draw option on it because it's a cleaner screen, and it gives me a much better idea. So you can see here, it's not much is shaded because the probability is so low. The p-value is low, and this matches our t-test value here. So in our conclusion, such a small p-value makes it unlikely that the low sample resulted from sampling error. So the odds of getting this sample, given that the null were true, is pretty low just based on variation. So we reject the null hypothesis. There is strong evidence that the mean amount of coffee dispensed by this machine is less than the stated 10 ounces. That should be an S. All right, this is also confirmed, if you remember from our last video, by our 95% confidence interval of 9.75 to 9.94 ounces, which is below 10. Don't forget, you can actually, it's a good idea, since it's not difficult, to run your confidence interval as well. All right, so let's go ahead and look at another example. This is a company has set a goal of developing a battery that lasts over 5 hours, 300 minutes, in continuous use. Based on the sample it left, is there evidence they met their goal? Okay, so first of all, our null hypothesis is that the mean is 300, all right, and that we want to show that we got more than 300, okay? So now let's look at the model. Remember, we want to check if it's random. Well, technically, this is not a random sample. This is like a pilot. They're developing the batteries, and this is like 12 that they've developed. But it's reasonable to assume that these 12 batteries are probably representative of the other batteries, at least with the current design. Independence is probably reasonable as well. And for the nearly normal condition, we're using n equals 12. So I've got one histogram here. This was automatically generated by my calculator when I put in that data. And it looks nearly uniform and pretty symmetric. So I would probably go there. I decided to go ahead and play with the windows a little bit. And you can see that you do have a little dip here. And I think this is good that we talk about it. Because how do we consider this? Well, this is still pretty normal. It's not like I really have two majorly separated peaks. If there was a bigger gap in the data, maybe I would be more concerned. And in fact, this is the solution from the book. And they have this histogram. And you can see that they have this little gap going on here. And what they called it was roughly unimodal and symmetric. So if you have a little dip going on, don't let that freak you out. You can still consider it roughly unimodal. All right, so now let's get to the calculations. Go ahead and run one var stats on your list of data, and you can see your average is 306.25. We have a S from our standard deviation from our sample is 29.31, and is 12, so our degrees of freedom is 11. Calculate the standard error by taking that and dividing by the square root of the sample size, and you get 8.461. Take your sample mean minus our null value here and divide by our standard error, and we get a t-value of 0.7387. Now you can use this to look up on the table the t-value, the probability that t with 11 degrees of freedom is greater than 0.7387, which we find is about 24%. It's admittedly much easier to use your calculator, and I'll show you how to do that now. So you go to test, and it's the second one. And luckily we have data, beautiful thing. Come down and put in our mu naught of 300. And we are using list 2, I believe. And then we want the battery life to be greater than 300. That's our alternate hypothesis. So I need to scroll down to this mu and hit enter, or it won't take. And then go down and hit draw. So I can get the nice clean view. And you can see that it's actually going to be quite a large number. So we calculated p-value of 0.2378 with a t-value of 0.7387. So we can also calculate a confidence interval or t-interval to make sure that this kind of jives with the data. It's really good advice to go ahead and do this. So we'll go ahead and calculate the t-interval. So you go down to number 8, t-interval, data, list, everything's set. I'll use 95%. I think the book used 90, but I like 90. 95 is good for this. So I have 287.63 to 324.87. So that's my confidence interval. So I feel pretty confident in my conclusion. The conclusion is, since the p-value is high, we fail to reject the null hypothesis. There is no evidence to suggest that the mean battery life exceeds 300 minutes. In other words, if I were to take a random sample of current batteries, not the new design, and did it, I'd have a 23% chance of matching the performance of the new design. So, or matching what we saw. It does not appear that the company has met its goal. And this is also confirmed by our 95% confidence interval, which includes 300 minutes. So this does not seem to see that 300 minutes is lower than the performance of these batteries. So last thing we need to do is determine sample size, and the formula is very similar, except we have t instead of z. And here's the twist. There's always a twist. Since we don't know all the values, usually we need to do a small pilot study. Good news, you don't have to do a small pilot study. Usually you'll get samples. They'll say, oh, here, this is from the small pilot study. All right. And you're going to use Z star on a first run, okay, to kind of calculate your first N. And then you're going to take that in and calculate your T. So I'll show you in this example. A company has set a goal of developing a battery that lasts over 300 hours, so over 5 hours, 300 minutes. So we want to do another trial, and we want to be 95% sure of estimating the mean lifespan within 15 minutes. So basically, what I did here, here's our normal formula. I put 1.96 for the 95% confidence interval, and we solve for n, and we got 14.67, so we round up 15, and our degrees of freedom are 14. We get a t-value of 2.145, and I calculated it using this command. Remember, it's always doing to the left on inverse t and inverse norm, so basically I took half of 5% and added it to the 95%. Okay, so now that we have our initial t-value, now I can do a better calculation of what I need. So I'm going to substitute in, still 15 is my margin of error, right? 15 minutes. Part of me was like, hey, that's not percent, but it's not because it's 15 minutes. 2.145, everything else is the same. Solve looks pretty much like that one, except now I have a new value here, and I get this n, which means I'm going to use n is 18. Now, don't forget, you want to be careful. There are many things that can go wrong in statistics. Maybe your data is really, really not normal. Be careful of multimodality. If there are 2 or more modes, and by that I mean like really separated, distinct modes, not maybe just a little peak in the mountain, it fails. If the data is very skewed, you can try re-expressing the data. You know, like you could take the logarithm or the square root. Set outliers aside, but remember to report on these individually. So if you have a big outlier that's messing up your data, you might need to pull it out, but save it for later. Remember, check how the sample was obtained. Check for bias. Make sure data are independent, and make sure data are from a randomized sample. And don't forget to interpret the confidence interval correctly. It's about the mean of the population, not about the means of the samples, not about individuals in the samples or individuals in the population.